Thank you very much to the organizers. Thank you to everyone who's here today. So in this presentation, I'm going to showcase some advantages of technical advances, not only to facilitate fieldwork, but in certain cases to make fieldwork even possible at all in inaccessible landscape types. So the Black Desert, which was mentioned in the title of northeastern Jordan, is locally called the Harra, and it is part of the Harrat Sham. This is a 50,000 square kilometer basalt plateau that reaches from southern Syria here to the northwest of Saudi Arabia. It was formed by volcanoes with lava flows that occurred between 30 million and 400,000 years ago, which was subsequently covered with loose sediment. A subsequent process called stone heaving, which is still quite a poorly understood geological phenomenon, has then brought these basalt blocks to the surface, resulting in a landscape covered in them. In this region, we've been conducting a survey called the Western Harra Survey, which the authors of this paper co-direct. It's been going since 2015, with so far 4 fieldwork seasons and 1 study season. Now, the landscape here is quite inaccessible, but it is not uniform. So a large part of the landscape is, like the picture in the top left shows, very densely covered in basalt blocks and cannot be traversed even by modern 4x4 vehicles. However, there are also areas that consist of larger wadi systems. These are seasonal river valleys, which provide sort of a modicum of access possibilities. Other areas are covered by large mud flats known locally as qayan, which also enable access into the basalt regions. And finally, some of the landscape is hilly limestone desert, which is also moderately accessible. But the geography of this region has always and still continues to this day to really closely dictate access possibilities. The Western Harra Survey is situated amongst the locations of other archaeological research in the region, as you can see on the map on the left. And for this research, aerial photography has always been fundamental to it, all the way from the earliest investigations onwards, starting with the pioneering photographs of Percy Maitland and others in the 1920s. So through these aerial surveys, several structures have been identified in this region that can be categorized into distinct types. You have, for example, the structures known as wheels, for obvious reasons, in the top left. Desert kites, well documented as being hunting infrastructure. Pendants, which are funerary complexes consisting of one large stone burial cairn and then a linear arrangement of stone piles emanating from it. Enclosures, which are sometimes singular and sometimes clustered in groups, and finally meandering walls, which are these low stone walls that stretch for kilometers across the desert for as yet an unknown purpose. Now, the methodology we developed for our project is based on other fieldwork projects that use remote sensing and GIS, but modified to fit our specific research goals and also the peculiarities of the landscape of the Black Desert. I'm not going to go into too much detail on that here, and you can see the complete version of this methodology online at bit.ly/WHS_methodology. But to explain briefly, we use existing fieldwork data, both excavation and survey data, and feed it into our GIS database. If it needs to be digitized, we do that. And we also use this existing fieldwork data to inform a remote sensing investigation that we conducted before the first fieldwork season. The results of this remote sensing investigation is then also fed into the GIS database, and we do analyses in order to plan our fieldwork. The data that we obtain from the fieldwork is then fed back into the same GIS database, and through further analyses, we then obtain our final results. I'll now show you in a bit more detail how this works. So before the first fieldwork season, I conducted a latitudinal line-by-line analysis of satellite imagery using the Google Earth platform at the satellite imagery's native resolution and marked any visible sites by both category and clarity. As a result of this, we found 2,770 possible features in the area, 1,157 of which were considered to be definite, so quite a lot. This analysis already allowed a slightly more detailed subdivision of some known site categories. For example, the sites known as wheels, we found that some of them are indeed wheel-like, as can be seen in the images in the top, with linear enclosure divisions emanating from the center, like the spokes of a wheel. Whereas others, which have been called wheels in the past, we have termed encircled enclosure clusters, or EECs for short. These are more like clusters of circular and subcircular enclosures, but with an encircling arrangement of very small enclosures. But this remote sensing survey in advance was most useful for planning the fieldwork. For starters, we could pinpoint a representative cross-section of sites in different landscape types to be visited on the ground. For example, here, the region marked as landscape type A is dense basalt desert. Region B is seasonal river valleys, wadis. Region C is a region with a lot of mud flats. And finally, region D is a hilly region. And we could select a nice cross-section of sites to visit to get a representative sample. The remote sensing survey was even more useful for the issue of accessing the selected sites. As mentioned, access in this region is mostly limited to natural features and also the occasional roads, which consist of a few, really just one or two asphalt roads, quite a few cleared tracks, vehicle tracks through the desert, the mud flats, and then finally the limestone desert. So what we did was to map all these areas and routes that are vehicle accessible and to calculate all identified sites within a 1 kilometer buffer of it. Without this, the majority of sites that provided data for very wide-reaching results would not have been able to be visited on the ground, since we simply would not have known how to access them. We applied several modern technologies in the field, most basically simply in order to locate sites. One of the peculiarities of this region is that sites are very hard to see on the ground. Even sites that are very clear on the satellite imagery, such as can be seen on the image on the left here, don't look very clear when you arrive at them on the ground. So the GPS geolocation of sites is absolutely necessary. Therefore, we put the entire database of our identified sites onto a Trimble device, which we carried with us in the field. And we also put it onto our personal laptop computers, along with offline satellite images using this free app, Orox Maps, which enabled easy navigation in the desert and also allowed us to make alterations if necessary to plan site visits and make decisions ad hoc in the field. By collaborating with the Royal Film Commission of Jordan, we were able to bring a drone into the country in April and September of 2019. And we planned flights with this drone in advance using the Drone Deploy app on our tablet computers. This helped with the precise documentation of specific sites by not only creating orthomosaics, but also digital elevation models, or DEMs, of their morphologies. For example, in the image in the top, there is quite a prominent cairn at the southern end of the wheel, which is not very clear on the orthomosaic, but is very obvious as a prominent feature marked in red on the DEM. On the encircled enclosure cluster at the bottom, it can be seen on the orthomosaic that some of the enclosing features seem to be rectangular with 90-degree angles, in contrast to the enclosures in the center. But this is far more clear on the DEM, which also enables us to see the shape of some enclosures which are not very clear on the orthomosaic because they're covered in basalt. So this process also aided in concretizing our morphological distinction of wheels and EECs. We could also use the data obtained by the drone to determine relative site chronology in some cases. For example, in this image, the orthomosaic is slightly unclear. It appears to be a kind of unusual wheel type of site with this strange kind of linear arrangement of stones coming out at a 90-degree angle here, and it's very unclear in the center. However, the DEM showed very clearly the true nature of this site. This is, in fact, a normal wheel upon which a pendant feature has been constructed at a later date. A third way that drones helped us in the field was the investigation of sites that are practically inaccessible. For example, this wheel site here, which is amongst particularly dense basalt rocks, and would be very difficult to access and is quite far from the nearest vehicle accessible area, the mudflats on the right. However, we could send over the drone from the nearest vehicle accessible location and produce high resolution imagery at a distance of more than 1 kilometer. This is, of course, not a replacement for any field visit, but it is a very good second best option, and it's certainly useful to determine whether a field visit would be worth the effort of accessing the site on foot. I'm now going to present a case study of one aspect of the research of the Western Harra Survey, where all elements of remote sensing, fieldwork, and the application of technologies are used together to produce results. And this case study is to do with ancient pathways cleared through the basalt. Now, already when we did our first survey of the satellite images, I noticed some light-colored lines that looked like linear clearings of stones, but it was not immediately obvious that they are connected to sites. A chance visit of some examples of these in the field produced a different picture of them. They appear to be obviously anthropogenic and appeared more often than not to link sites. So we then reviewed the satellite imagery on the basis of this new information. Now, of course, there are many types of routes in the desert, but luckily they are all morphologically distinct and thus able to be categorized. You have the modern vehicle tracks, which are very wide and very straight. We have these so-called sheep tracks. These are tracks that are naturally created by the feet of sheep pushing to the side small stones as they are herded across the desert. These are obviously very narrow and they're also quite irregular. And finally, the likely pre-modern pathways, which are wider than the sheep tracks, not as wide as the modern vehicle tracks, and slightly more linear than the sheep tracks, but not as linear as the modern vehicle tracks. And in this one small area you can see on the right, we managed to map all three types very clearly. So with this data, we carried out a larger mapping and analysis of pre-modern pathways in a test area of the Western Harra Survey. And the analysis showed, in fact, that the main purpose of these routes seemed to be firstly to enable long-distance movement by connecting natural access features such as the seasonal water valleys and the mudflats to other features of the same kind, so to enable sort of a hopping across the desert via these natural access features connected via anthropogenic paths. And secondly, they were to allow easy access from sites to these access features and also to resources, for example, water resources, which are, again involve connecting to seasonal water valleys and the mudflats, and also some material resources, which I'll come back to in a minute. So to connect back to site morphologies, these pathways also appear to be more frequently connected to EECs than other site types. But again, the drone data was found to be very helpful in analyzing the pathways. For example, by distinguishing them from the sheep tracks in certain cases where width and straightness-based morphological distinctions were not found to be sufficient. So, for example, in this image here, you can see several tracks surrounding this very nice wheel site, which all appear to have roughly a similar width and a similar degree of linearity. However, on the digital elevation model, only one of these paths has a significant signature. And when we looked at the wider satellite imagery, it was also seen that this is the only path which connects this site to a natural access feature, in this case, a mudflat around 1 kilometer to the east. So it is likely that this path is the only anthropogenic one and the rest are sheep tracks. The drone data was also found to be useful to corroborate some hypotheses surrounding cleared paths, which we formed in the field. For example, this pathway here was interpreted by us to be arranged in deliberate steps. The treads of the steps are circled in white, leading up the bank of a wadi. Now, this was first noticed in the field. However, the drone imagery we subsequently took showed very clearly that this path constitutes steps. And we can see that the white lines mark the continuation of the path, and it shows the connection of it to the nearby site 1745 and how it enables access from the wadi to it. To take these analyses further, we subsequently visited and walked along the entire length of the longest path observed on the satellite imagery, a 6-kilometer long north-south path connecting a large mudflat to a large wadi, a seasonal river valley, which was likely part of a much longer route. We experimented by timing how long it took to walk along the path and how long it took to walk along the same trajectory, but right next to the path over the basalt rocks. And we found that walking on the path, we were 20% faster. This showcases the definite advantage of these anthropogenic pathways to traversing the basalt. Walking along the path also enabled the identification of factors invisible to remote sensing. For example, we found that there were abundant flint sources at the wadi at the bottom end of the path, called the Wadi Rajil at the southern end here, which was likely at least a contributing purpose for the pathway's creation to enable easy access. Secondly, we also were able to identify sites of abundant petroglyphs, as can be seen in the bottom right, and also some small cairns that were too small to detect on satellite imagery. On the image on the left, you can see that all the sites marked in green were identified for the first time in the field and were invisible to remote sensing. Furthermore, the locations and prominence of some of these cairns that we identified along the path raised the possibility that for at least some, their purpose was facilitating path recognition, since it is actually quite hard to see the trajectory of these paths from the ground, even when you're standing on them. And we noticed several cairns that were in alignment to the path, including some that were beyond the actual route of the path, but in exactly the same trajectory. And we also experienced firsthand how they could be used for navigation. Therefore, this could also very likely have been a purpose for these cairns in the past. To summarize, it's very clear that the benefits of this new technology enable us not only to facilitate, but in certain cases to even enable research in the first place in landscapes of inaccessibility. It also enables the fieldwork to be systematic due to in advance remote sensing-based planning, for example, being able to select representative cross-sections of site types to visit. It also makes sites accessible that otherwise would not be, by the mapping of access routes that would otherwise be unknown, and also by the flying of drones over long distances. And finally, by integrating all aspects in a holistic fashion, much further reaching interpretations can be made that are still very much grounded in solid research identifications, as we can be seen from the example of the long pathway. Thanks very much for listening, and in the top right, you can see the links where you can follow the Western Harra Survey online. Thank you.